My name is Dylan DeLeon, and in our thermal regulation conference, talking about evaporation rates over surface area. So the purpose of the experiment was to look at different variants, and we had two. We had surface area to volume ratio, and then we also had exposure to H2O. And so um, one of our pipes was misted with water, as you can see in this picture right here. And that was to simulate sweating or people or animals in terrestrial environments that can get water to cool down. And so, as you can see, we used a hot plate to heat two pipes, and then one was they were both set on a piece of paper towel, and then one was exposed to water, and the other one was not. And once they stopped increasing in heat, once after they got to 50 degrees Celsius, then we started taking data, and that was every 30 seconds for 5 minutes. So here's some raw data, and even without even looking at any numbers, it's pretty drastic. You can tell how very different each of these different slopes are. And so this is going to be the cylinder pipe, and then this is going to be with water right here and without water right here. And then this is the elliptic cylinder, and this is without water and with water. And so you can tell just by just because of the surface area to volume ratio that there is a drastic increase in the slope. Now we're going to analyze some data. And so we went ahead and found the average equation of the line. And so this is the regular copper pipe with H2O right here, and then without H2O right here. And so it's at 2.3 without and 2.6. So that's going to be it's a 0.5 increase in the slope, which is a pretty drastic increase. And then once we get over and look at the elliptic cylinder, it's even more drastic. And so we have 3.6 for our starting slope and then 4.7. And so our slope is going to be our dependent variable because that is the rate at which heat is dissipated out of the pipe. And as you can see from this data, that the surface area had a drastic effect because even the base without water is one entire unit over the cylinder pipe with H2O. And then when we look at the elliptic cylinder with water, it's 4.7, which is nearly double the others. And so we can really see the effect that surface area and evaporation with water has on temperature change. So here's the conclusion. The results of this experiment really did confirm what we've been learning in class about the surface area to volume ratio. And when we apply this to other aspects of science besides like pipes, we can understand how organisms are. And so if you're a small organism with a high surface to volume ratio, you're as you can tell from these results, you're going to be drastically more affected by the outside environment. And so that's going to lead you to be more ectothermic because you're going to require a lot of energy in order to maintain a constant body heat if you have a high surface to volume ratio. And then just like how whenever we sweat, we basically coat ourselves in a small layer of water in order to help the heat dissipate. That's why we sweat when we're hot. And so my closing conclusion is the pipe with the bigger surface area to volume ratio dissipate the heat faster due to the increased area for heat to be exposed to the outside environment, while when covered with water, simulating sweating, the results showed that the evaporation, the heat dissipated even faster. Thank you.